Why are the biggest stars impossible? Tonight, we're going to explore a cosmic giant so massive it challenges everything we thought we knew about how stars work. You've probably heard about massive stars before. Betelgeuse, VY Canis Majoris, names that pop up in space documentaries. But here's what most people don't realize. There's a star out there so impossibly large that according to our best physics, it simply shouldn't exist. By the end of this journey, you're going to understand exactly why the largest star ever discovered is breaking the fundamental rules of stellar physics. Before we dive in, if you enjoy these kinds of cosmic explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Let's begin. Humans perceive objects by instinctively comparing them to our own bodies, standing roughly 5 feet 7 inches tall on average. This fundamental reference point shapes everything we understand about scale and proportion. When we encounter something massive like a redwood tree stretching 300 feet into the sky, our minds automatically calculate that it towers nearly 50 times our height. Even then, we can still wrap our consciousness around such dimensions because they remain within the realm of earthly experience. Consider Mount Everest, rising 29,029 feet above sea level. To us, it represents the ultimate expression of terrestrial grandeur, an almost incomprehensible monument of rock and ice that has challenged human ambition for generations. Yet, when we place Everest within the broader context of our planet's features, it begins to shrink in significance. The Himalayan mountain range itself spans roughly 1,550 miles, making Everest merely one peak among countless others in a geological formation that dwarfs any single human construction. Expanding our perspective further, entire continents reveal scales that strain our intuitive understanding. Asia covers approximately 17 million square miles, an area so vast that if you could walk across it at a steady pace of 3 miles per hour for 12 hours each day, the journey would consume decades of continuous travel. The sheer enormity of such land masses begins to challenge our ability to form meaningful mental images. We can recite the numbers, but truly grasping what 17 million square miles represents pushes against the boundaries of human comprehension. Our planet Earth itself measures 7,118 miles in diameter, a figure that sounds manageable until you attempt to visualize traversing that distance. If you could somehow drill straight through the Earth's core and emerge on the opposite side, the journey would span nearly 8,000 miles of solid rock, molten metal, and crushing pressure. To put this in perspective, if Earth were shrunk to the size of a basketball, our tallest mountains would disappear entirely, becoming invisible irregularities on what would appear as a perfectly smooth sphere. But Earth represents merely the beginning of our cosmic journey into incomprehensible scales. If we maintain that basketball-sized Earth, our Sun would appear as a sphere measuring 358 feet in diameter, roughly the height of a 35-story skyscraper. This comparison reveals something profound about our cosmic neighborhood, the object that governs our entire existence, providing the energy for every living thing on our planet, is almost unimaginably larger than the world we inhabit. The Sun contains 99 to 86% of all the mass in our solar system, gravitationally dominating a space that extends trillions of miles in every direction. This stellar furnace operates at temperatures that exceed anything in human experience. A single point on the solar surface reaches 10,340 degrees Fahrenheit, hotter than any industrial furnace ever constructed on Earth. The nuclear reactions occurring in the Sun's core generate temperatures of 27 million degrees Fahrenheit, conditions so extreme that matter exists in states completely foreign to earthly physics. Light from this cosmic inferno travels at 186 to 282 miles per second, yet still requires 8 minutes and 20 seconds to traverse the 93 million miles separating us from our star. This delay means we never see the sun as it exists in the present moment, but always as it appeared more than 8 minutes ago. The energy striking Earth each second could power human civilization for millions of years, yet represents only a tiny fraction of the sun's total output, most of which radiates uselessly into the void of space. Jupiter, the largest planet in our solar system, demonstrates the sun's overwhelming dominance. This gas giant, with its diameter of 88,846 miles, could contain 1,300 Earth-sized planets within its volume. Yet Jupiter itself could fit inside the sun more than 1,000 times over. The largest object in our planetary system becomes insignificant when compared to our star, revealing the profound hierarchy of cosmic scales. Despite its impressive size relative to Earth and the other planets, our Sun represents nothing more than a modest yellow dwarf star of spectral class G2V, considered small by stellar standards. Astronomers classify it as utterly ordinary, one star among hundreds of billions in our galaxy alone. The nearest star to our solar system, Proxima Centauri, lies 24 light-years away, a distance of approximately 25 trillion miles. To comprehend this separation, consider that if you could travel at the speed of Voyager 1, humanity's fastest spacecraft, the journey to our nearest stellar neighbor would require 73,000 years of continuous flight. Our Milky Way galaxy contains an estimated 400 billion stars, most of them significantly larger and more massive than our Sun. These stellar giants exist at distances so profound that their light, racing toward us at the ultimate cosmic speed limit, requires thousands or millions of years to reach our telescopes. We observe these distant suns not as they are, but as they were when human civilization was young or when our species didn't even exist. Contemplating these scales produces what philosophers call conceptual vertigo, a dizzy sensation that arises when the mind attempts to grasp dimensions far beyond evolutionary experience. Our brains develop to navigate environments measured in miles and feet, to track prey across landscapes spanning dozens of miles, to build shelters measured in yards. We possess no neural circuitry designed to process cosmic distances or stellar masses. Yet this journey into incomprehensible scale has barely begun. Beyond our ordinary sun lie stellar monsters so enormous that our star would appear as a grain of sand compared to a football. The physics of stellar formation reveals that under certain conditions, stars can grow to sizes that challenge our mathematical ability to describe them meaningfully. Spectroscopic data confirms the existence of stars with radii 2,000 times larger than our Sun, objects so vast they defy easy categorization. Modern astronomical instruments extend our senses far beyond their natural limitations. The Very Large Telescope Interferometer measures stellar diameters with precision of milli-arcseconds, resolving details on stellar surfaces separated by thousands of light-years. Infrared radiometers detect thermal energy from giant stars across galactic distances, while space telescopes like Hubble capture images of extended stellar atmospheres that writhe and pulse with barely contained energy. Each observation reveals that the universe operates on scales that exist completely outside human experience. Astrophysicists calculate stellar masses by observing the gravitational dance of binary star systems, measuring how massive objects bend spacetime itself. Spectroscopy decomposes starlight into its component wavelengths, revealing the chemical composition and temperature of stellar atmospheres across impossible distances. Photometry tracks brightness variations that indicate pulsations and instabilities in stars whose surfaces could engulf entire planetary systems. Space missions like the Parker Solar Probe venture into the solar wind, studying magnetic fields and particle streams on microscopic scales, while orbiting an object whose true scale defeats human comprehension. Computer simulations model stellar interiors using relativistic hydrodynamics, attempting to understand processes occurring at pressures and temperatures that exist nowhere else in the local universe. Recent discoveries suggest that some stars exceed every theoretical limit established by current physics. The largest known star challenges our fundamental understanding of stellar formation and gravitational stability, existing in apparent violation of principles we thought were universal. These cosmic giants force us to reconsider everything we believed we knew about how matter behaves under extreme conditions. Understanding such extreme scales compels a profound reevaluation of humanity's place in the cosmos. We are forced to confront the reality that our entire existence unfolds on dimensions that barely register against the backdrop of cosmic immensity. Yet paradoxically, this recognition of our cosmic insignificance simultaneously reveals our unique significance as conscious observers capable of measuring and contemplating scales that transcend all direct experience. This journey from the familiar to the incomprehensible exposes the fundamental limits of human perception when confronted with cosmic immensity. We stand at the threshold of discoveries that will challenge not only our understanding of stellar physics, but our basic concepts of what constitutes reality itself. The largest star ever discovered awaits our exploration, an object so impossibly vast that its very existence calls into question the laws of nature themselves. To truly comprehend the magnitude of stellar giants that challenge physical law, we must first establish our Sun as a cosmic measuring stick. Our familiar star possesses a mass of 485 x 10^30 pounds, equivalent to 333,000 times the mass of Earth. This seemingly incomprehensible number becomes our baseline for understanding objects that dwarf even our life-giving star. The Sun's average density of 0.51 pounds per cubic inch makes it only 40% denser than water, a startling revelation that highlights how stellar matter behaves under extreme gravitational compression. Deep within the solar core, temperatures reach 27 million degrees Fahrenheit, creating conditions where hydrogen nuclei overcome their natural electromagnetic repulsion and fuse into helium. These thermonuclear reactions occur under pressures 250 billion times greater than Earth's atmospheric pressure at sea level, crushing matter into states that exist nowhere else in our immediate cosmic neighborhood. Every second, these fusion reactions convert 5 billion pounds of matter directly into pure energy, following Einstein's famous equation E = mc². To grasp the scale of this transformation, imagine compressing all of humanity, every person who has ever lived, into a sphere matching the density of the solar core. The entire population of our species throughout history would fit within a sphere measuring just 16 feet in diameter. This thought experiment reveals not only the extreme density of stellar cores, but also the almost incomprehensible energy densities required to sustain nuclear fusion across astronomical timescales. The total energy radiated by our Sun equals 1 x 10^26 horsepower, comparable to detonating 100 billion hydrogen bombs every single second for 10 billion years. Each square foot of the solar surface emits 850,000 watts of energy, more than most industrial power plants generate in their entirety. This energy output remains remarkably stable, varying by less than 0.1% over decades of careful measurement, demonstrating the extraordinary precision with which gravitational and thermal forces balance within stellar interiors. Individual sunspots, dark regions where magnetic field lines suppress convection, can span diameters exceeding 30,000 miles, easily encompassing the entire Earth several times over. These apparently minor features on the solar surface represent magnetic phenomena more powerful than anything achievable in terrestrial laboratories. During solar maximum, coronal mass ejections hurl billions of pounds of plasma into space at speeds reaching 1–2 million miles per hour, creating disturbances that affect technological systems across our entire planet. The solar magnetic field extends far beyond Pluto's orbit, creating a heliosphere that spans trillions of miles and shields our solar system from high-energy cosmic radiation. This invisible bubble of magnetic influence demonstrates how stellar effects propagate across distances that dwarf planetary scales, establishing spheres of influence that encompass multiple planetary systems. Voyager 1, humanity's most distant spacecraft, crossed the heliopause at a distance of 11 billion miles from Earth, finally entering true interstellar space after traveling for over 3 decades. When compared to red dwarf stars, our Sun appears gigantic. Proxima Centauri, our nearest stellar neighbor, contains only 12% of the solar mass and measures 124,000 miles in radius, small enough that our Sun could contain nearly 7,000 Proxima Centauri-sized objects. These diminutive red dwarfs burn hydrogen fuel so slowly they can maintain fusion for trillions of years, far exceeding the Sun's expected 10 billion-year lifetime. Yet, despite their longevity, red dwarfs represent stellar minimalism, barely massive enough to sustain nuclear reactions. Their surfaces glow at temperatures between 3,500 and 6,000 degrees Fahrenheit, giving them the characteristic red coloration that dominates their spectral output. Stars like our Sun, classified as G-type main sequence stars, constitute only 7% of all stars in the Milky Way galaxy. Most stars are actually red dwarfs, smaller and cooler than our Sun, while a precious few are massive giants that burn brilliantly for relatively brief periods. The stellar mass function reveals that for every star like our Sun, approximately 12 red dwarfs exist, making our apparently ordinary star actually quite rare in cosmic terms. Brown dwarfs, sometimes called failed stars, possess masses between 13 and 80 Jupiter masses, insufficient to ignite sustained hydrogen fusion in their cores. These substellar objects glow dimly from gravitational compression alone, generating surface temperatures between 1,800 and 5,000 degrees Fahrenheit through the slow release of gravitational potential energy. They represent the boundary between planets and true stars, existing in a twilight realm where nuclear physics yields to gravitational thermodynamics. At the opposite extreme, neutron stars compress the mass of two 17 suns into spheres measuring only 12 miles in diameter. These stellar remnants achieve density so extreme that a teaspoon of neutron star material would weigh 13 billion pounds on Earth. The gravitational field of a neutron star is so intense that an object dropped from 1 foot above the surface would strike at nearly 4–5 million miles per hour. Neutron stars spin at rates exceeding 700 rotations per second, creating lighthouses in space as their magnetic fields sweep beams of radiation across interstellar distances. White dwarfs, the remnant cores of stars like our Sun, pack stellar masses into objects roughly Earth-sized, achieving densities of 1,800 pounds per cubic inch. These stellar corpses represent the final fate awaiting our own star in approximately 5 billion years, when nuclear fuel exhaustion causes the solar core to collapse while the outer layers expand and then eventually drift away. A white dwarf's surface gravity is approximately 350,000 times stronger than Earth's, meaning that a 180-pound person would weigh 63 million pounds on its surface. Stellar black holes concentrate masses between 3 and 20 solar masses into points of theoretically infinite density, creating gravitational fields so powerful that not even light can escape once it crosses the event horizon. These exotic objects represent the ultimate compression of matter, where conventional physics breaks down and space-time itself becomes curved beyond recognition. Near a stellar black hole, tidal forces would stretch a human body into a thin stream of particles long before reaching the event horizon, a process astronomers grimly term spaghettification. Now expanding our vision toward truly large stars, our Sun begins to appear minuscule. Red giant stars like Arcturus possess radii 26 times larger than the Sun, while maintaining much lower average densities. These evolved stars have exhausted hydrogen fuel in their cores, causing them to expand dramatically as helium fusion begins under different temperature and pressure conditions. Arcturus spans 18.6 million miles in diameter, yet contains only slightly more mass than our Sun, resulting in an average density thousands of times lower than solar density. During its own red giant phase, our Sun will expand until its surface engulfs the orbits of Mercury and Venus, transforming from a compact yellow dwarf into a bloated red giant spanning 186 million miles in diameter. This expansion occurs as the stellar core contracts and heats up, while the outer layers cool and expand to maintain thermal equilibrium. The transformation demonstrates how stellar evolution fundamentally alters the relationship between mass, size, and energy output. Earth itself may survive this phase, though its surface will be scorched beyond recognition by the proximity of the expanded solar photosphere. Red supergiants represent massive stars in the final stages of stellar evolution, having progressed through multiple phases of nuclear burning in their cores. These stellar giants begin life with masses exceeding 8 times that of our Sun, burning through their nuclear fuel at prodigious rates. Betelgeuse, the distinctive red star marking Orion's shoulder, possesses a radius approximately 950 times larger than our Sun. If Betelgeuse replaced our Sun, its surface would extend beyond Mars's orbit, engulfing the inner solar system in a tenuous but scorching stellar atmosphere, reaching temperatures of 6,000 degrees Fahrenheit. The scale of Betelgeuse becomes apparent when we consider that light traveling at its ultimate speed limit requires nearly 4 hours to traverse the star's diameter. A commercial airliner flying at 500 miles per hour would need over 400 years to complete a single circuit around Betelgeuse's equator. The star's volume could contain approximately 1.6 billion objects the size of our Sun, yet its total mass equals only 11. 6 solar masses creating an average density less than 1/10,000th that of Earth's atmosphere at sea level. Antares, the red supergiant heart of Scorpius, measures between 680 and 800 solar radii, making it visible to the naked eye despite lying 550 light-years from Earth. This stellar monster radiates energy at a rate 75,000 times greater than our Sun, yet its surface temperature of only 6,000 degrees Fahrenheit gives it the characteristic red coloration that earned its name, meaning rival of Mars. Antares represents a star in its death throes, having exhausted hydrogen and helium in its core and now burning heavier elements in nested shells surrounding a collapsing iron core. VY Canis Majoris, once considered the largest known star, stretches 1,420 times the solar radius, creating a sphere so vast that light traveling at 186.82 miles per second requires over 6 hours to traverse its diameter. If placed at the center of our solar system, VY Canis Majoris would extend beyond Jupiter's orbit, encompassing the 4 inner planets and the asteroid belt within its tenuous outer atmosphere. This dying star loses mass at an extraordinary rate, shedding the equivalent of Earth's mass every million years through intense stellar winds that create a complex nebula of expelled material. These scales begin to shatter our intuitive understanding of what constitutes a normal star. Objects like VY Canis Majoris exist at the extreme limits of stellar physics, where radiation pressure approaches the gravitational binding force. that holds the star together. Such massive stars lose material through intense stellar winds reaching velocities of 60 miles per second, shedding solar masses of matter annually as they approach the theoretical limits of stellar stability. The material expelled from these dying giants enriches interstellar space with heavy elements forged in stellar cores, providing the raw materials for future generations of stars and planets. Yet even these supergiants pale in comparison to the true hypergiants that push stellar physics to its absolute breaking point, objects so large they shouldn't exist according to our current understanding of how stars form and maintain stability across cosmic time. Red giants emerge when stars exhaust the hydrogen fuel in their cores and begin the complex process of helium fusion. This evolutionary transition represents one of the most dramatic transformations in stellar physics, fundamentally altering everything about a star's structure, appearance, and behavior. The process begins when hydrogen burning can no longer sustain the outward radiation pressure needed to balance gravitational collapse. As the core contracts under its own weight, temperatures and pressures increase dramatically, while the outer atmospheric layers paradoxically expand to enormous proportions. The expansion occurs because the stellar core contracts and heats up, while the outer layers simultaneously cool and expand, creating a delicate balance between competing physical forces. Surface temperatures drop to between 5,000 and 7,200 degrees Fahrenheit, giving these evolved stars their characteristic red coloration. This dramatic cooling of the stellar photosphere shifts the peak wavelength of emitted light toward the red end of the electromagnetic spectrum, making these stars appear distinctly different from their main sequence predecessors. Average densities in red giant stars fall drastically during this expansion phase, often becoming less dense than Earth's atmosphere at sea level. This extreme dilution of stellar material creates objects that are simultaneously massive and incredibly tenuous, existing in states that challenge our intuitive understanding of what constitutes solid matter. The gravitational field at the surface of these expanded stars becomes so weak that atmospheric material can easily escape into interstellar space. Aldebaran, the bright orange star marking the eye of Taurus the Bull, possesses a radius 44 times larger than our Sun, demonstrating the scale of typical red giant expansion. This stellar giant provides a preview of our Sun's own future appearance in approximately 5 billion years, when hydrogen exhaustion forces similar evolutionary changes. At 65 light-years from Earth, Aldebaran appears as one of the brightest stars in our night sky, despite being a relatively nearby example of red giant evolution. The variation among red giants reveals the complex relationship between stellar mass, age, and evolutionary state. Epsilon Pegasi stretches to a radius 185 times larger than our Sun, showing that even among normal giants, extreme size differences exist. This star demonstrates how slight variations in initial mass and metallicity can produce dramatically different evolutionary outcomes, creating stars that dwarf our Sun yet maintain surprisingly similar core masses. Gamma Crucis, prominently visible in the Southern Cross constellation, radiates energy at a rate 1,500 times greater than our Sun, while maintaining a surface temperature significantly cooler than solar values. This apparent contradiction illustrates how stellar luminosity depends on both temperature and surface area, with the enormous photospheric area of red giants more than compensating for their reduced surface temperatures. These evolved stars continuously lose mass through stellar winds of unprecedented scale and duration. The weak gravitational binding at their surfaces allows atmospheric material to escape at rates reaching 1/10,000,000th of a solar mass per year for typical red giants. Over the millions of years these stars spend in their giant phase, this gradual mass loss fundamentally alters their structure and eventual fate, determining whether they will become white dwarfs, neutron stars, or undergo more exotic evolutionary pathways. The low surface gravity characteristic of red giants creates escape velocities measured in tens rather than hundreds of miles per second, allowing even relatively cool atmospheric gases to achieve sufficient speeds to leave the star permanently. This ongoing mass loss enriches the surrounding interstellar medium with processed stellar material, contributing to the chemical evolution of galaxies over cosmic timescales. Variable red giants like Mira Ceti demonstrate how these evolved stars exist in states of dynamic instability. Mira pulsates with a period of 332 days, during which its brightness can vary by factors exceeding 1,000 between maximum and minimum phases. These dramatic changes occur as the stellar atmosphere alternately expands and contracts in response to complex interactions between radiation pressure, gravitational forces, and opacity variations in the stellar envelope. The size variations accompanying Mira's pulsations span radii between 300 and 400 times that of our Sun, meaning this single star periodically expands and contracts across dimensions larger than Earth's entire orbit. During maximum expansion phases, Mira's photosphere reaches temperatures allowing the formation of complex molecules and dust grains that would be instantly vaporized in hotter stellar environments. Hydrae represents another class of pulsating red giant with a period of 361 days and brightness variations spanning 7 astronomical magnitudes. These semi-regular variables demonstrate how stellar pulsations can drive complex atmospheric dynamics, creating shock waves that propagate through tenuous outer layers and trigger episodes of enhanced mass loss. Carbon-rich giants like Y. Canum venaticorum possess atmospheres fundamentally altered by nuclear processing in their cores. These stars synthesize carbon through the triple alpha process, where 3 helium nuclei combine under extreme temperature and pressure conditions to form carbon-12. Convective dredge-up episodes transport this newly synthesized carbon from the stellar interior to the photosphere, dramatically altering the atmospheric chemistry and creating conditions favorable for the formation of complex carbon-bearing molecules. The presence of carbon-rich material in stellar atmospheres enables the condensation of graphite and silicon carbide dust grains, which absorb and re-emit stellar radiation in characteristic patterns. These dust clouds can become so dense they temporarily obscure the underlying star, as demonstrated by R. Coronae Borealis, a carbon giant that undergoes sudden declines in brightness lasting months or years when carbon soot condenses in its atmosphere. Symbiotic giants like CH Cygni exist in binary systems where mass transfer between stellar components creates exotic environments unlike anything seen in isolated stars. The interaction between a red giant primary and a white dwarf companion creates accretion disks, stellar winds, and recurrent nova explosions that fundamentally alter the evolution of both stars. These systems demonstrate how stellar evolution becomes increasingly complex when gravitational interactions between nearby objects influence the process. Red giants in globular clusters provide unique laboratories for studying stellar evolution under conditions of extremely low metallicity. The cluster 47 Tucanae contains thousands of red giants with ages approaching 13 billion years, representing some of the oldest stars in the observable universe. These ancient giants reveal how stellar evolution proceeded when the universe contained far fewer heavy elements than exist today, demonstrating the fundamental role of metallicity in determining stellar structure and lifetime. The European Space Agency's Gaia mission has revolutionized our understanding of red giant stars by measuring precise parallax distances for hundreds of thousands of these objects throughout our galaxy. These measurements reveal the true scale and distribution of red giant populations, confirming theoretical predictions about their luminosities and establishing them as crucial standard candles for determining galactic structure and distance scales. Asteroseismology, the study of stellar oscillations, has transformed red giant astronomy by revealing internal structures impossible to observe directly. The Kepler Space Telescope discovered oscillation modes in hundreds of red giants, providing detailed information about their internal rotation, magnetic fields, and mass distribution. These pulsations act as seismic waves that probe stellar interiors, revealing how convection and rotation interact in the expanded envelopes of evolved stars. The oscillation data reveals that red giant cores rotate much faster than their outer layers, indicating that angular momentum transport becomes extremely inefficient during the giant phase. This differential rotation creates complex magnetic field geometries that influence mass loss rates and atmospheric dynamics in ways still being investigated by stellar astrophysicists. Red giant observations also provide crucial insights into stellar population synthesis and galactic chemical evolution. The abundance patterns observed in red giant atmospheres reflect both primordial composition and nuclear processing throughout stellar lifetimes, allowing astronomers to reconstruct the star formation history and chemical enrichment of galactic regions over billions of years. The study of red giants in different galactic environments reveals how metallicity, age, and stellar density influence evolutionary outcomes. Giants in the galactic halo show different size and luminosity distributions compared to disk giants, reflecting the different formation conditions and stellar populations that characterize these galactic components. Modern spectroscopic surveys can now analyze thousands of red giants simultaneously, revealing subtle variations in surface composition that reflect different mixing processes and mass loss histories. These observations show that apparently similar red giants can have dramatically different internal structures and evolutionary fates, depending on factors like initial rotation, magnetic field strength, and binary interactions that are often difficult to determine from external observations alone. Red giants represent merely the first step toward understanding the most extreme stellar objects in the universe, serving as stepping stones toward the true supergiants that challenge the very foundations of stellar physics. Supergiants represent stars born with initial masses exceeding 8 times that of our Sun, embarking on evolutionary pathways that unfold with breathtaking rapidity compared to smaller stars. These stellar giants burn through their hydrogen fuel reserves in mere 10 to 50 million years, a cosmic instant compared to the 10 billion year lifetime awaiting our Sun. This accelerated evolution occurs because massive stars operate under such extreme internal conditions that nuclear fusion proceeds at rates thousands of times faster than in lower mass stars. The relationship between stellar mass and lifetime follows an inverse power law that creates one of astronomy's most striking paradoxes. The most massive stars, despite containing vastly more fuel, exhaust their nuclear reserves far more quickly than their smaller cousins. A star with 20 solar masses burns hydrogen at rates roughly 40,000 times faster than our Sun, compressing billions of years of stellar evolution into time frames shorter than the existence of complex life on Earth. Rigel, the brilliant blue supergiant marking Orion's foot, exemplifies the extreme conditions characterizing these stellar monsters. With a mass of 21 suns, Rigel radiates energy at a rate 120,000 times greater than our star, while maintaining surface temperatures exceeding 36,000 degrees Fahrenheit. This combination of mass and temperature creates luminosity so intense that Rigel remains clearly visible to the naked eye despite lying 860 light-years from Earth, demonstrating how supergiant luminosity can overcome even vast interstellar distances. The scale of energy production in stars like Rigel defies easy comprehension. Each second, this single star radiates more energy than our Sun produces in 3 years of continuous fusion. If Rigel were placed at the same distance from Earth as our Sun, its radiation would instantly vaporize our planet's atmosphere and melt the rocky surface within minutes. The star's output equals the simultaneous detonation of 12 trillion hydrogen bombs every second, maintained continuously for millions of years. Deneb, another blue supergiant prominently visible in the constellation Cygnus, possesses an estimated mass of 19 suns, but has evolved to a radius 203 times larger than our star. This expansion indicates that Deneb has already progressed beyond the main sequence phase, beginning the complex nuclear burning processes that characterize supergiant evolution. Despite its enormous distance of 2,600 light-years, Deneb shines with the brightness of a first-magnitude star, radiating energy at 200,000 times the solar rate. Blue supergiants maintain surface temperatures between 36,000 and 90,000 degrees Fahrenheit, creating stellar atmospheres where familiar chemical processes break down entirely. At these temperatures, hydrogen exists almost entirely as individual protons and electrons, while heavier elements undergo multiple ionization stages that produce spectral line patterns, unlike anything observed in cooler stellar environments. The extreme luminosity of blue supergiants creates stellar winds of unprecedented intensity, removing mass at rates approaching 1/1,000,000th of a solar mass per year. These winds achieve terminal velocities exceeding 19 million miles per hour, fast enough to traverse the diameter of Earth in under 4 minutes. The kinetic energy carried by these stellar winds exceeds the total energy output of entire star-forming regions, creating vast bubbles of hot, low-density gas that can span hundreds of light-years in diameter. Radiation pressure in blue supergiants approaches the theoretical Eddington limit, where outward radiation pressure begins to balance inward gravitational attraction. This critical threshold occurs when stellar luminosity becomes so intense that photons carry sufficient momentum to counteract gravitational binding, creating conditions of marginal stability that can trigger dramatic instabilities in stellar structure. The Eddington limit represents a fundamental constraint in stellar physics, establishing maximum luminosities that stars can sustain without losing gravitational control over their outer layers. For massive stars approaching this limit, small fluctuations in nuclear burning rates or atmospheric opacity can trigger episodes of enhanced mass loss or dramatic brightness variations that fundamentally alter stellar evolution. Red supergiants emerge when massive stars exhaust central hydrogen burning and expand to enormous proportions, while cooling dramatically. These evolved giants represent the final stable burning phases available to stars, massive enough to synthesize elements heavier than helium in their cores. Mu Cephei, known as Herschel's garnet star for its distinctive deep red coloration, stretches to radii between 972 and 1,260 times larger than our Sun. If placed at the center of our solar system, Mu Cephei would engulf the orbits of all terrestrial planets and extend beyond the asteroid belt, reaching nearly to Jupiter's orbit. This stellar giant maintains surface temperatures of only 5,800 degrees Fahrenheit, cool enough to allow the formation of complex molecules and dust grains in its extended atmosphere. The star's deep red appearance results from this low temperature, which shifts peak emission toward longer wavelengths while dust absorption preferentially removes blue light. KW Sagittaria, with an estimated radius of 1,460 times that of our Sun, rivals the largest known stars while demonstrating the extreme mass loss characteristic of red supergiants. This stellar giant radiates energy at 360,000 times the solar rate, despite its relatively cool surface temperature, achieving this enormous luminosity through sheer photospheric area. The star's extended atmosphere exists in a state of continuous outflow, losing mass equivalent to Earth's weight every few thousand years. WOHG 64, located in the Large Magellanic Cloud, spans between 1,240 and 1,130 solar radii, while surrounded by a complex nebula created by extreme mass loss episodes. High-resolution images from the Very Large Telescope reveal intricate structures in the circumstellar material, including dense knots, filamentary extensions, and asymmetric brightness patterns that indicate complex magnetic field interactions or the presence of an unseen stellar companion. The nebula surrounding WOHG 64 extends across dimensions measured in light-years, containing material equivalent to several solar masses expelled during recent episodes of enhanced mass loss. Spectroscopic analysis reveals that this ejected material includes elements synthesized in the stellar core during advanced burning phases, enriching the surrounding interstellar medium with carbon, oxygen, and heavier elements crucial for planet formation and biological chemistry. NML Cygni represents another candidate for the largest known stars, with radius estimates exceeding 1,600 times that of our Sun. Water vapor and silicon monoxide masers detected in its atmosphere provide precise tools for measuring stellar dimensions, as these molecular emission lines occur under very specific temperature and density conditions that can be modeled to determine atmospheric structure and size. Maser emission occurs when stellar radiation pumps molecules into excited states that then emit coherent radiation at specific frequencies, creating natural amplification systems that can be detected across vast interstellar distances. These cosmic lasers provide unique probes of stellar atmospheres, revealing temperature gradients, velocity fields, and chemical abundances in the extended envelopes of supergiant stars. The Westerlund 1 cluster, located 11,500 light-years from Earth, contains some of the most massive stars known in our galaxy, including the red supergiant Westerlund 126. This young cluster provides a laboratory for studying massive star evolution under conditions of high stellar density, where gravitational interactions and shared radiation fields can influence individual stellar development in ways impossible to observe in isolated star formation regions. Westerlund 126 and its cluster companions demonstrate how the most massive stars form in groups, emerging from giant molecular clouds with masses sufficient to produce multiple stellar giants simultaneously. The cluster environment creates feedback effects where stellar winds and eventual supernova explosions from the most massive members influence the evolution of nearby stars, creating complex interconnections between individual stellar fates. Semi-regular variable supergiants like Scorpii demonstrate the atmospheric instabilities characteristic of these extreme stellar environments. Pulsating with a period of 714 days, Scorpii varies between magnitudes 7, 34, and 9, 2, corresponding to brightness changes of nearly a factor of 7. These variations result from complex interactions between radiation pressure, atmospheric opacity, and gravitational forces in the star's extended envelope. The pulsational instabilities affecting red supergiants create shock waves that propagate through their tenuous atmospheres, triggering episodes of enhanced mass loss and dust formation. These shock-driven phenomena can create dramatic changes in stellar appearance over timescales of years or decades as atmospheric conditions shift between states favoring different molecular chemistries and dust condensation processes. IRC plus 10420, a yellow hypergiant that recently lost mass equivalent to 5 solar masses, exemplifies the extreme instability characterizing the most luminous stars. Spectroscopic observations reveal emission lines indicating optically thick stellar winds, where expelled material becomes so dense it obscures the underlying stellar photosphere. This star exists in a transitional phase between stable hydrogen burning and the explosive phases that will ultimately destroy it. These observations demonstrate that supergiants exist in states of constant marginal stability, where small changes in nuclear burning rates, atmospheric opacity, or magnetic field strength can trigger dramatic structural reorganizations. The most massive supergiants spend their final evolutionary phases in cycles of expansion, mass loss, and contraction that can fundamentally alter their observable properties over human timescales. But we have not yet reached the absolute physical limits of what stars can become. Hypergiants represent the most extreme stellar objects that can exist, while maintaining any semblance of stability, dwelling perilously close to the Humphreys-Davidson limit, an empirical boundary that defines the maximum luminosity stars can achieve without destroying themselves through their own radiation pressure. These cosmic monsters exist in such rarefied conditions that fewer than several dozen confirmed hypergiants are known throughout our entire Milky Way galaxy, making them among the most exotic and unstable objects in the observable universe. The Humphreys-Davidson limit emerges from decades of observational astronomy, revealing a conspicuous gap in the Hertzsprung-Russell diagram, where no stable stars exist. This forbidden zone occurs at luminosities exceeding approximately 600,000 times that of our Sun, combined with surface temperatures below 18,000 degrees Fahrenheit. Stars that venture into this region undergo catastrophic instabilities that fundamentally alter their structure, often ejecting substantial portions of their mass in explosive events that can briefly outshine entire star-forming regions. P Cygni serves as the prototype for luminous blue variables, a class of hypergiants characterized by dramatic eruptions that eject solar masses of material in spectacular displays of stellar instability. Historical records document P Cygni's transformation from a barely visible star to one of the brightest objects in the night sky during eruptions spanning decades. During these violent episodes, P Cygni ejected material equivalent to 15 solar masses, creating an expanding nebula that remains visible today as testament to the star's explosive past. These eruptions occur when radiation pressure approaches the Eddington limit, creating conditions where stellar winds can no longer maintain steady outflow rates. Instead, the star experiences episodic mass ejection events, where large fractions of the stellar envelope are expelled at velocities exceeding 400,000 miles per hour, creating shock waves that heat the expelled material to temperatures of millions of degrees and generate X-ray emissions detectable across interstellar distances. Eta Carinae experienced perhaps the most dramatic hypergiant eruption in recorded history during the Great Eruption of 1837-1856, when this distant star temporarily became the second brightest object in Earth's night sky, despite lying over 7,500 light-years away. During this extraordinary event, Eta Carinae ejected the famous Homunculus Nebula, containing approximately 40 solar masses of material expelled at velocities reaching 400 miles per second. The energy released during Eta Carinae's great eruption approached that of a supernova explosion, yet the star survived intact and continues to shine today with a luminosity 5 million times greater than our Sun. Modern observations reveal Eta Carinae as a binary system containing stars with masses of 90 and 30 times that of our Sun, orbiting each other with a period of 5 years in an intricate gravitational dance that may have triggered the historic eruption through tidal interactions. The current luminosity of Eta Carinae places it among the most energetic single objects known, radiating more power than entire globular clusters containing hundreds of thousands of stars. Each second, this hypergiant releases energy equivalent to the simultaneous detonation of 500 trillion hydrogen bombs, sustained continuously for millions of years through nuclear reactions occurring under conditions that push the boundaries of known physics. The Pistol star, located near our galaxy's center, demonstrates how hypergiants can achieve luminosities that exceed theoretical expectations by substantial margins. This blue hypergiant once blazed with the intensity of 10 million suns, creating radiation fields so intense they could photoionize hydrogen gas across distances of hundreds of light years. The star's past activity ejected the Pistol Nebula, containing 10 solar masses of processed stellar material expelled approximately 4,000 years ago during a period of extreme instability. LBV 1806-20 exemplifies the observational challenges inherent in studying hypergiants, with luminosity estimates ranging between 2 and 40 million times that of our Sun. This enormous uncertainty reflects the difficulties astronomers face when attempting to measure distances through the dense interstellar dust that obscures the galactic plane, where many of the most massive stars reside. The extinction caused by intervening dust can reduce apparent brightness by factors of thousands, making accurate distance determinations extremely challenging. Despite these observational difficulties, LBV 1806-20 clearly represents one of the most luminous stars known, possibly exceeding the theoretical maximum luminosity by factors of 10 or more. If confirmed at the upper end of estimated luminosities, this star would challenge fundamental assumptions about stellar physics, suggesting that current theoretical models fail to account for conditions existing in the most extreme stellar environments. Peony star, designated WR1POUKA, demonstrates another pathway to hypergiant status through the Wolf-Rayet phase of stellar evolution. With a luminosity 3, 2 million times greater than our Sun, this star maintains surface temperatures exceeding 90,000 degrees Fahrenheit while losing mass at rates that will completely strip its outer layers within a few 100,000 years. The star's spectrum shows broad emission lines characteristic of stellar winds moving at several percent of the speed of light. Yellow hypergiants represent perhaps the rarest and most unstable stellar phase, exemplified by Rho Cassiopeia, which underwent sudden dimming in 1946-1947 when it ejected material equivalent to several Earth masses in a brief but dramatic instability episode. During this event, the star's surface temperature dropped by over 1,800 degrees Fahrenheit as shock waves propagated through its extended atmosphere, creating conditions that favored the condensation of dust grains and temporarily obscured the stellar photosphere. HR 5171A presents a unique case study as a contact binary system where two yellow hypergiants share a common envelope, creating a combined radius of 1,300 times that of our Sun. Tidal interactions between the stellar components distort both stars into extreme elliptical shapes, while mass transfer between them creates accretion streams and hotspots that produce complex light variations and spectroscopic signatures unlike anything observed in isolated stars. Yellow hypergiants like HR 5171I represent transitory phases lasting only a few thousand years, during which massive stars transition between stable blue supergiant phases and final red supergiant evolution. These brief evolutionary episodes occur when stellar cores undergo structural reorganization, as nuclear burning progresses from hydrogen to helium fusion, creating temporary imbalances between radiation pressure and gravitational forces that manifest as dramatic changes in stellar appearance. Pulsational instabilities characterize most hypergiant phases, creating periodic variations in brightness and mass loss that can span timescales from months to decades. These oscillations occur when the stellar envelope becomes marginally stable against radial perturbations, leading to cycles of expansion and contraction that drive enhanced mass loss during maximum phases. VX Sagittarii exemplifies the observational uncertainties plaguing hypergiant astronomy, with radius estimates exceeding 1,520 solar radii, but carrying substantial measurement uncertainties. The star's spectral classification varies between M4 and M10 Ia, indicating extreme variations in surface temperature that suggest ongoing structural instabilities or complex atmospheric dynamics that current stellar models cannot fully explain. The variability observed in VX Sagittarii and similar hypergiants may result from multiple factors including pulsational instabilities, episodic mass loss events, dust cloud formation and dissipation, or magnetic field interactions that create complex atmospheric phenomena. These variations can span several astronomical magnitudes, corresponding to brightness changes of factors exceeding 100 between maximum and minimum phases. VY Canis Majoris held the title of largest known star for many years, though recent observations have refined estimates of its radius to only 1,120 times that of our Sun. High-resolution imaging reveals that VY-CMA is surrounded by an extremely complex circumstellar nebula, showing evidence for multiple episodes of asymmetric mass ejection, spanning thousands of years of stellar evolution. Hubble Space Telescope images of VY Canis Majoris reveal intricate structures, including arcs, knots, and filamentary extensions that indicate highly asymmetric mass loss processes. These patterns suggest that magnetic fields, stellar rotation, or the presence of an unseen companion star influence the geometry of material ejection, creating preferential directions for mass loss that produce the observed nebular complexity. Red hypergiants like VY Canis Majoris represent the final stable burning phases available to the most massive stars before they either explode as supernovae or undergo direct gravitational collapse to form black holes. Mass loss rates in these objects can reach 1/10,000th of a solar mass per year, sufficient to remove the entire stellar envelope within 100,000 years and fundamentally alter the star's ultimate fate. The extreme mass loss characterizing hypergiant evolution occurs through a combination of radiation-driven winds, pulsation-enhanced outflows, and episodic eruptions that can eject substantial fractions of the stellar mass in single events. This ongoing mass loss creates vast circumstellar nebulae that can span several light-years in diameter while containing dozens of solar masses of enriched material that will eventually contribute to future generations of star formation. But a recent discovery challenges everything we thought we knew about maximum stellar limits. Stephenson 2-18 was discovered in 2012 during a systematic survey of red supergiant stars emerging from observational data as an object so extraordinary that it fundamentally challenges our understanding of stellar physics. Located in the constellation Scutum at approximately 19,000 light-years from Earth, this stellar giant belongs to the Stephenson 2 cluster, one of the most massive stellar associations known in our galaxy. The discovery represents a watershed moment in astronomy, revealing an object whose very existence appears to violate established theoretical frameworks governing stellar formation and stability. The Stephenson 2 cluster itself presents unique characteristics that make it a natural laboratory for studying extreme stellar evolution. This remarkable stellar association contains 26 confirmed red supergiants, representing the highest concentration of such massive evolved stars found anywhere in the Milky Way. The cluster's unusual composition suggests it formed under extraordinary conditions that favored the production of extremely massive stars, creating an environment where stellar physics operates at the absolute limits of possibility. The cluster's location deep within the galactic plane exposes it to intense gravitational fields and complex magnetic environments that may have influenced the formation and evolution of its constituent stars. Stellar densities within the cluster reach levels where gravitational interactions between individual stars become significant, potentially triggering enhanced mass loss episodes or unusual evolutionary pathways not observed in more isolated stellar environments. Radio observations conducted by the Australia Telescope Compact Array provided the first accurate measurements of Stephenson 2·18's dimensions, revealing a radius approximately 2,150 times larger than our Sun. This measurement, obtained through interferometric techniques that can resolve stellar surfaces across vast interstellar distances, established Stephenson 2·18 as the largest known star by volume, surpassing all previous record holders by substantial margins. The interferometric observations required extraordinary technical precision, combining signals from multiple radio telescopes separated by distances of several miles to achieve angular resolution measured in thousandths of arcseconds. This technique allows astronomers to measure stellar diameters with accuracy comparable to reading newspaper headlines on the Moon from Earth, demonstrating the remarkable capabilities of modern observational astronomy. If Stephenson 2·18 were placed at the center of our solar system, its photosphere would extend far beyond Saturn's orbit, reaching nearly to Uranus at a distance of 1.8 billion miles from the central fusion core. The star's total volume could theoretically contain approximately 10 billion objects the size of our Sun, creating a sphere of stellar material so vast it challenges human comprehension. Light traveling at its ultimate speed of 186 thus to 82 miles per second would require over 4 or 5 hours to traverse the star's diameter, longer than a typical workday on Earth. To put this scale in perspective, if you could somehow drive a car at highway speeds of 70 miles per hour continuously around Stephenson 2·18's equator, the journey would require over 2,900 years to complete. A commercial airliner flying at 500 miles per hour would need approximately 400 years for a single circumnavigation, while even the fastest spacecraft ever built by humanity would require decades to traverse the star's diameter. The estimated diameter of Stephenson 2·18 reaches an astounding 1.8 billion miles, making it larger than the orbit of Saturn and approaching dimensions comparable to the distance between Earth and Uranus. This scale places the star in a category entirely separate from conventional stellar objects existing in realms where normal stellar physics begins to break down under the extreme conditions created by such enormous atmospheric volumes. Despite its incredible size, Stephenson 2·18 maintains a luminosity of approximately 440,000 times that of our Sun, making it visible even through the dense interstellar dust that characterizes the galactic plane where it resides. This luminosity, while enormous by terrestrial standards, represents a remarkably low value given the star's vast surface area, indicating surface temperatures significantly cooler than smaller but more luminous hypergiants. The energy output of Stephenson 2·18 equals approximately 17x 10^32 watts, equivalent to the simultaneous detonation of 440 billion hydrogen bombs every second for millions of years. Yet this staggering energy production rate is distributed across such an enormous surface area that each square mile of the stellar photosphere emits only about as much energy as a small terrestrial city consumes annually. Surface temperatures of only 5,800 degrees Fahrenheit explain Stephenson 2·18's deep red coloration and place it among the coolest massive stars known. This low temperature creates atmospheric conditions where water vapor, titanium oxide, and complex silicate molecules can exist in stable forms, producing the characteristic spectral features that allow astronomers to identify and study red supergiants across galactic distances. The cool surface temperature enables chemical processes impossible in hotter stellar atmospheres, allowing the condensation of dust grains and the formation of complex molecules that would be instantly dissociated in more energetic environments. Water molecules detected in the stellar spectrum indicate atmospheric conditions similar to those in cool stellar winds, where molecular chemistry can proceed despite the extreme scale of the stellar environment. The current mass of Stephenson 2-18 is estimated between 12 and 25 solar masses, a figure that seems impossibly small given the star's enormous volume. This dramatic discrepancy between mass and size indicates an average density lower than Earth's upper atmosphere at altitudes exceeding 60 miles, creating conditions where stellar material exists in states more tenuous than any achievable in terrestrial laboratories. The extremely low density implies that most of Stephenson 2-18's apparent volume consists of material so tenuous it barely qualifies as matter in any conventional sense. The average density throughout the stellar envelope approaches values typical of the best laboratory vacuums, yet this rarefied material maintains sufficient opacity to create the observed thermal emission and absorption line spectra. Spectroscopic analysis reveals emission lines from water vapor and silicon monoxide molecules that form in the star's extended atmosphere, providing crucial diagnostics for understanding the physical conditions in these extreme environments. Silicon monoxide masers detected in the stellar envelope indicate current mass loss rates of approximately 30 Earth masses per year, demonstrating how these giant stars continuously shed material into the surrounding interstellar medium. The maser emission occurs when stellar radiation pumps molecular transitions into population inversions, creating natural amplification systems that can be detected across vast interstellar distances. These cosmic lasers provide unique probes of stellar atmospheric structure, revealing velocity fields, temperature gradients, and density distributions in regions too distant and tenuous for direct observation by other means. The extended atmospheric structure of Stephenson 2-18 creates what astronomers term a pseudo-photosphere, where the apparent stellar surface lies far above the actual fusion-burning core. This extended envelope consists of material so tenuous that its density approaches that of the best laboratory vacuums, yet it contains enough matter to create the observed spectral signatures and thermal emission patterns. Current theoretical models struggle to explain how such extended atmospheres can maintain stability against gravitational collapse or dispersal into interstellar space. The delicate balance between radiation pressure, stellar winds, and gravitational attraction must operate with extraordinary precision to prevent either immediate collapse or explosive mass ejection that would destroy the stellar structure entirely. Detailed modeling using sophisticated radiative transfer codes like DUSTY indicates that Stephenson 2-18's envelope contains substantial amounts of silicate dust grains condensed from material expelled during earlier evolutionary phases. These microscopic particles absorb stellar radiation and re-emit it at infrared wavelengths, creating the complex thermal signature that allows astronomers to map the star's extended structure. The dust component plays crucial roles in determining atmospheric opacity and driving mass loss through radiation pressure effects. Silicate grains, formed through condensation of silicon, oxygen, and metals in the cooling stellar wind, absorb efficiently at optical wavelengths while re-emitting at infrared frequencies, creating a natural mechanism for converting stellar radiation into mechanical energy that drives continued mass loss. Distance measurements to Stephenson 2-18 remain problematic due to its association with the Stephenson 2 cluster, introducing significant uncertainties into calculations of the star's true luminosity and size. Parallax measurements are impossible at such distances, forcing astronomers to rely on cluster membership and statistical distance estimates that can vary between 16,000 and 22,000 light-years, depending on the assumed cluster properties. The distance uncertainty directly affects all derived stellar parameters, including luminosity, radius, and mass loss rates. If Stephenson 2-18 lies at the far end of the estimated distance range, its true luminosity could exceed theoretical limits by even larger margins, further emphasizing the challenges this object poses to conventional stellar physics. Recent proper motion measurements suggest the possibility that Stephenson 2-18 may not actually be a member of the Stephenson 2 cluster, potentially placing it at different distances that would dramatically alter its calculated luminosity. If the star lies at greater distances than currently assumed, its true luminosity could exceed 630,000 times that of our Sun, pushing it even further into regions of parameter space where no stable stars should exist, according to current theoretical frameworks. Spectroscopic variability observed over timescales of years indicates ongoing atmospheric changes that may reflect pulsational instabilities, episodic mass loss events, or complex magnetohydrodynamic phenomena operating in the star's extended envelope. These variations provide crucial insights into the physical processes maintaining such extreme stellar structures against gravitational collapse while revealing the dynamic nature of hypergiant atmospheres. Strong infrared emission detected by space-based telescopes reveals extensive dust clouds heated by stellar radiation to temperatures of several hundred degrees Fahrenheit. The spatial distribution and thermal properties of this circumstellar material provide evidence for the star's mass loss history and the complex interactions between stellar winds and previously expelled material that create the observed nebular structures. Comparative studies with other known hypergiants reveal Stephenson 2-18 as an extreme outlier, possessing characteristics that place it in a unique category among stellar objects. No theoretical models of stellar evolution predict the existence of stars with this combination of large size, low temperature, and apparent stability, suggesting fundamental gaps in our understanding of massive star physics that extend far beyond simple parameter uncertainties. Current theories of stellar evolution fail to explain how stars can maintain such enormous atmospheric envelopes without undergoing immediate gravitational collapse or explosive mass ejection. The Humphreys-Davidson limit supposedly prevents the existence of stable stars with such high luminosities and cool surface temperatures, yet Stephenson 2-18 appears to violate this fundamental constraint with apparent impunity, forcing astronomers to reconsider basic assumptions about stellar structure and evolution. Its existence forces a complete revision of models describing the evolution of supermassive stars, revealing new frontiers in our understanding of cosmic phenomena that extend far beyond current theoretical capabilities. The Eddington limit establishes the maximum luminosity, where radiation pressure balances gravitational attraction, creating a fundamental boundary that defines the upper limits of stellar stability. For a star with solar mass, this critical threshold corresponds to approximately 38,000 times the luminosity of our Sun. Beyond this limit, radiation pressure becomes so intense that it overcomes gravitational binding, causing the star to literally blow itself apart through its own energy output. Yet Stephenson 2-18 appears to exceed this fundamental limit by a factor of more than 10, creating a physical paradox that challenges our most basic understanding of how stars can exist. The classical Eddington limit assumes that stellar radiation interacts with matter primarily through Thomson scattering, where photons bounce off free electrons in the stellar atmosphere. This interaction transfers momentum from radiation to matter, creating outward pressure that must be balanced against gravitational attraction for stellar stability. When luminosity approaches the Eddington value, radiation pressure becomes so strong that it can launch stellar winds with velocities approaching a significant fraction of the speed of light. Stephenson 2-18's apparent violation of the Eddington limit forces astronomers to reconsider fundamental assumptions about stellar physics. If this star truly maintains the observed luminosity while preserving structural integrity, it suggests that current theoretical frameworks dramatically underestimate the complexity of radiation-matter interactions in extreme stellar environments. The star's existence implies that nature has found mechanisms to circumvent what physicists considered inviolable physical laws. The Humphreys-Davidson limit defines an observational boundary between stable and unstable massive stars, marking a region in the Hertzsprung-Russell diagram where no normal stars should exist. This empirical limit indicates that stars with luminosities exceeding approximately 600,000 solar luminosities and surface temperatures below 18,000 degrees Fahrenheit cannot maintain stable configurations for extended periods. The forbidden zone remains virtually empty except for a few anomalous objects like luminous blue variables during their brief eruptive phases. No conventional stellar evolution model predicts stable stars in the parameter space occupied by Stephenson 2-18, where high luminosity combines with extremely cool surface temperatures. Current theories suggest that such objects should either explode immediately through radiation-driven instabilities or collapse under their own gravity, within timescales much shorter than stellar evolution processes. The persistent existence of Stephenson 2-18 demonstrates that our understanding of stellar physics remains fundamentally incomplete. Spectral line opacity effects can modify the classical Eddington limit significantly, particularly in cool stellar atmospheres, where metal atoms retain multiple electrons and produce thousands of absorption lines. In these environments, metals can provide opacity values 10 to 100 times greater than Thomson scattering alone, creating conditions where radiation pressure operates through fundamentally different mechanisms than those assumed in standard stellar models. The modified Eddington limit accounting for spectral line opacity may permit luminosities up to 10 times higher than classical predictions, potentially explaining how stars like Stephenson 2-18 can achieve such extreme energy output without immediate self-destruction. However, even this enhanced limit falls short of explaining the most extreme properties observed in this remarkable star, suggesting that additional physical processes must contribute to its stability. Dense stellar winds can create pseudo-photospheres where the apparent stellar surface lies far above the actual fusion-burning core, potentially creating the illusion of enormously inflated stellar radii. In this scenario, what appears as an extended stellar atmosphere actually represents a dense outflow of material that becomes optically thick at large distances from the central star. This mechanism could account for some of the apparent size of Stephenson 2-18 while maintaining compatibility with conventional stellar physics. External convective zones in supergiant stars can extend through 60 to 70% of the total stellar mass, creating conditions where energy transport occurs through bulk motion of stellar material, rather than radiative diffusion. Convective energy transport allows the existence of much more extended stellar envelopes than would be possible through radiation alone, potentially enabling the formation of structures as large as those observed in Stephenson 2-18. The efficiency of convective energy transport depends critically on the temperature and density gradients within stellar envelopes, parameters that remain poorly constrained in the most extreme supergiant stars. Modern stellar evolution codes struggle to model convection in such extended, low-density environments where traditional mixing length theory may break down entirely and require fundamentally new approaches to fluid dynamics in stellar interiors. Pulsational instabilities can temporarily inflate stellar atmospheres by extreme factors, creating episodic expansion phases where stars achieve radii far larger than their equilibrium values. Strange mode pulsations predicted by theoretical models but never conclusively observed could drive expansion events that maintain enlarged stellar configurations for extended periods, potentially explaining the extreme size of objects like Stephenson 2-18. These exotic pulsation modes arise from complex interactions between radiation pressure, atmospheric opacity, and gravitational forces in the extended envelopes of massive stars. The driving mechanism involves radiation, becoming trapped in atmospheric layers where opacity increases with expansion, creating feedback loops that can sustain large amplitude oscillations for thousands of years. Extreme mass loss can remove stellar envelopes faster than expansion processes can inflate atmospheric structures, creating a complex interplay between stellar evolution and structural stability. Stars approaching the Eddington limit experience mass loss rates that can strip entire atmospheric envelopes within hundreds of thousands of years, fundamentally altering their evolutionary pathways and creating transient configurations not predicted by standard stellar models. The blue ward evolution that follows red supergiant phases typically prevents indefinite growth of stellar radii as core nuclear burning progresses through heavier elements and drives changes in stellar structure that favor contraction rather than expansion. Stars with cores exceeding 60% of their total mass generally abandon the supergiant sequence entirely, evolving toward Wolf-Rayet configurations or immediate core collapse. Binary star interactions can dramatically modify stellar evolution and final appearance, creating configurations that single-star models cannot predict. Mass transfer in close binary systems can inflate one stellar component to anomalous sizes, while stripping material from its companion, potentially creating objects that superficially resemble isolated hypergiants, but actually result from complex gravitational interactions between multiple stellar components. Common envelope evolution represents an extreme form of binary interaction where one star expands to engulf its companion, creating shared atmospheric structures that can achieve sizes rivaling the largest known single stars. During this phase, orbital energy dissipation can drive dramatic changes in both stellar components, potentially creating the extreme configurations observed in objects like Stephenson 2-18. Stellar rotation creates centrifugal forces that oppose gravitational attraction, establishing an omega limit, where rotational velocity becomes sufficient to disrupt stellar structure entirely. Rapidly rotating massive stars can achieve equatorial velocities approaching their breakup limits, creating oblate configurations where centrifugal forces fundamentally alter stellar structure and energy transport processes. Magnetic fields can modify convective structure and energy transport throughout stellar interiors, creating conditions where standard stellar evolution models fail to predict actual stellar behavior. Magnetic pressure can provide additional support against gravitational collapse, while magnetic braking can alter rotation rates and stellar structure evolution in ways that current theoretical frameworks cannot fully describe. Magnetic activity similar to solar coronal mass ejections but scaled to supergiant proportions could inflate stellar atmospheres through mechanisms analogous to those operating in our Sun, but amplified by factors of millions. Magnetic reconnection events in supergiant magnetospheres might release energy sufficient to drive atmospheric expansion and maintain extended configurations against gravitational collapse. Non-equilibrium thermodynamics in highly extended stellar atmospheres remains poorly modeled, with current theoretical approaches assuming local thermodynamic equilibrium conditions that may not apply in environments where radiation and matter interact weakly across vast spatial scales. The breakdown of equilibrium assumptions could fundamentally alter predictions about atmospheric structure and stability in the most extreme stellar environments. Equations of state for low-density gases under intense radiation fields prove inadequate for modeling conditions in objects like Stephenson 2-18, where matter exists in regimes intermediate between conventional stellar atmospheres and interstellar space. The behavior of partially ionized gases at densities approaching laboratory vacuum conditions while subjected to radiation fields millions of times more intense than solar radiation remains largely unexplored territory in theoretical physics. Molecular opacities in cool stellar atmospheres are known only approximately, with significant uncertainties in the temperature and density dependence of absorption coefficients for complex molecules like water vapor and titanium oxide. These opacity uncertainties translate directly into uncertainties in stellar structure calculations, potentially explaining some of the discrepancies between theoretical predictions and observed properties of extreme supergiants. Three-dimensional convection models reveal behaviors not predicted by traditional one-dimensional stellar evolution theory, including the formation of large-scale circulation patterns, temperature inversions, and complex mixing processes that can dramatically alter stellar structure and evolution. Modern computational fluid dynamics simulations suggest that convection in supergiant envelopes operates through mechanisms fundamentally different from those assumed in conventional stellar models. Large-scale turbulence in extended stellar atmospheres can create structures and phenomena completely unanticipated by current theoretical frameworks, potentially maintaining atmospheric configurations that appear impossible according to standard stability analysis. Turbulent pressure support might provide additional mechanisms for maintaining extended stellar envelopes against gravitational collapse. The formation of multiple convective layers generates recently observed phenomena that challenge traditional stellar structure theory, creating complex internal dynamics where different atmospheric regions can evolve semi-independently and interact through mechanisms not captured in conventional stellar evolution codes. Stephenson 2-18 may represent stellar physics that current science simply cannot comprehend, existing as a natural laboratory where matter behaves according to principles that extend far beyond our present theoretical capabilities. A journey at the speed of light would require 4 hours to traverse completely across Stephenson 2-18, longer than most domestic flights, and equivalent to traveling from New York to London at humanity's ultimate velocity limit. This seemingly simple measurement reveals the profound disconnect between human-scaled experience and cosmic reality. Light, which can circle Earth's equator 7 times in a single second, requires the better part of a working day to cross this single stellar object, demonstrating scales that begin to overwhelm our capacity for meaningful comprehension. Traveling at Earth's escape velocity of 25,000 miles per hour, crossing Stephenson 2-18's atmosphere would demand 180 years of continuous flight, spanning multiple human generations. This journey would exceed the entire recorded history of the United States, requiring travel times longer than humanity has possessed powered flight. The comparison reveals how stellar dimensions exist in temporal frameworks that dwarf individual human lifespans and challenge our ability to conceptualize duration itself. If we could somehow drive continuously at highway speeds of 62 miles per hour, circumnavigating Stephenson 2-18's equator would require 3,300 years of constant travel without rest or refueling. This duration exceeds recorded human civilization, spanning from the Bronze Age collapse to the present day. The journey would witness the rise and fall of empires, the development of writing, mathematics, and science, yet still not approach completion of a single circuit around this stellar giant. The surface area of Stephenson 2-18 exceeds that of 50 billion Earth-sized planets, creating a spatial expanse that challenges our most fundamental concepts of magnitude. If every square mile of Earth's surface could somehow be populated with 1 million people, and then this population density were maintained across Stephenson 2-18's entire photosphere, the resulting civilization would contain more individuals than atoms in the observable universe. Such comparisons break down because human language lacks adequate frameworks for describing truly cosmic scales. Surface gravity on Stephenson 2-18 measures approximately 400,000 times weaker than Earth's gravitational field, creating conditions where an astronaut would weigh less than the paper in a business card. This extraordinarily weak gravitational binding approaches the effective vacuum of space, where matter barely clings to the stellar surface and can escape with velocities lower than a gentle breeze. The gravitational environment resembles conditions in the outer reaches of planetary magnetospheres rather than the surface of a massive star. The average density throughout Stephenson 2-18 equals only 0.02% of Earth's atmospheric density at sea level, creating material states more tenuous than the best laboratory vacuums, while somehow maintaining sufficient opacity to produce observable stellar spectra. This paradoxical combination of enormous scale and virtually absent material density represents conditions that exist nowhere else in human experience and challenge fundamental assumptions about what constitutes matter itself. Every second, Stephenson 2-18 radiates energy equivalent to detonating 1 trillion hydrogen bombs simultaneously, maintaining this rate continuously for millions of years through nuclear fusion processes occurring in its distant core. This energy output exceeds the total electrical generation capacity of human civilization by factors of billions, yet represents merely the normal operation of stellar physics at extreme scales that dwarf terrestrial energy production. The total energy emitted by Stephenson 2-18 in a single day surpasses humanity's cumulative energy consumption over the past 100 billion years, including all fossil fuels burned, nuclear reactors operated, and renewable energy harvested throughout our species' existence. This comparison demonstrates how stellar energy production operates on scales that make human civilization appear as an insignificant fluctuation in cosmic energy budgets. Material ejected annually through stellar winds equals the mass of 270 Earths, creating mass loss rates that exceed the total matter content of entire planetary systems. This continuous outflow removes material equivalent to replacing our entire planet nearly once per day, demonstrating how hypergiants like Stephenson 2-18 exist in states of constant material flux that fundamentally alter their surrounding environments across galactic distances. The escape velocity at Stephenson 2-18 surface measures less than normal human walking speed, meaning that an astronaut could literally walk off the stellar surface and drift into interstellar space without requiring rocket propulsion. This remarkable condition arises from the extreme size and low mass density combination, creating gravitational environments unlike anything that exists elsewhere in the known universe. Atmospheric pressure at the stellar photosphere measures billions of times lower than conditions at the top of Mars's tenuous atmosphere, yet somehow maintains sufficient density to support the chemical processes that create observed spectral features. The pressure environment resembles the most extreme high-altitude conditions achievable in terrestrial laboratories, yet extends across volumes larger than planetary systems. The gravitational field becomes so weak that microscopic dust particles can float freely through the stellar atmosphere without settling toward the surface, creating permanent suspension of solid material in environments that nominally represent the surface of a massive star. These conditions challenge conventional definitions of stellar atmospheres and demonstrate how extreme scale creates physical environments that operate according to principles unlike anything in terrestrial experience. If Stephenson 2-18 possessed a planetary system, its theoretical habitable zone would extend beyond Neptune's orbit at distances exceeding 3 billion miles from the stellar core. This vast region of potentially life-supporting temperatures demonstrates how stellar giants create environmental conditions on scales that dwarf our entire solar system, yet the extreme stellar winds and radiation fluctuations would likely prevent stable planetary formation in such environments. Light emitted from nuclear reactions in the stellar core requires 48 minutes to travel through the extended atmosphere and reach the visible photosphere, indicating that observed stellar brightness reflects fusion processes that occurred nearly an hour earlier. This light travel time exceeds the duration of most university lectures and approaches the length of feature films, demonstrating how even electromagnetic radiation requires significant time to traverse these cosmic giants. Standing hypothetically on Stephenson 2-18 surface, the horizon would lie approximately 500,000 miles distant, farther than the distance between Earth and Moon. This enormous horizon distance creates curvature so gradual that the stellar surface would appear completely flat to human observers, resembling an infinite plane rather than the surface of a spherical object. The gentle curvature challenges human spatial perception and creates environments where familiar concepts like up and down lose meaningful definition. A solar day on Stephenson 2-18 would last decades due to the extremely long rotational period characteristic of evolved giant stars, where tidal forces and stellar winds have gradually slowed rotation to nearly imperceptible rates. Sunrise and sunset would occur on timescales comparable to human career spans, creating day-night cycles that extend across multiple generations of terrestrial observers. Gravitational tidal forces remain imperceptible even to the most sensitive instruments, as the enormous size creates such gradual gravitational gradients that differential forces become virtually undetectable across human-scale dimensions. An astronaut orbiting near the stellar surface would experience tidal effects weaker than those created by distant planets in our solar system. Temperature variations between equatorial and polar regions span less than 90 degrees Fahrenheit, remarkably uniform considering the star's enormous size and complex internal dynamics. This thermal uniformity results from efficient energy transport through the extended convective envelope, creating surface conditions more stable than those found on Earth despite the extreme stellar environment. The stellar atmosphere extends millions of miles beyond the visible photosphere, creating circumstellar environments that blur the boundary between stellar surface and interstellar space. These extended atmospheric regions contain material densities intermediate between stellar atmospheres and interstellar medium, occupying vast volumes where conventional physics struggles to describe material behavior. Convective cells within the stellar atmosphere operate on scales larger than Jupiter, with individual circulation patterns spanning dimensions comparable to entire planetary systems. These enormous convective structures transport energy and material across distances measured in millions of miles, creating atmospheric dynamics that operate on scales beyond anything observed in planetary atmospheres. Convective circulation cycles require years to complete single upward-downward flows, creating atmospheric turnover timescales comparable to orbital periods of outer planetary systems. Material rising from deeper atmospheric layers may require decades to reach maximum altitude before beginning descent cycles, demonstrating how atmospheric dynamics in stellar giants operate according to temporal frameworks that exceed human lifespans. Magnetic fields throughout Stephenson 2-18 remain so weak they would be undetectable by any terrestrial magnetometer, creating conditions where electromagnetic forces become negligible compared to gravitational and radiation pressure effects. The weak magnetic environment allows charged particles to move freely through the stellar atmosphere without significant electromagnetic constraints. Sound waves propagating through the stellar structure require months to traverse completely from core to surface, creating acoustic environments where disturbances travel at speeds measured in miles per hour rather than the thousands of feet per second characteristic of terrestrial sound propagation. Stellar seismology operates on timescales comparable to seasonal changes on Earth. Radial pulsations characteristic of variable giant stars operate with periods measured in years or decades, creating brightness variations that unfold over timescales longer than human educational careers. Individual pulsation cycles span durations comparable to economic recessions or political administrations, demonstrating how stellar variability operates on temporal scales that challenge human perception of periodic phenomena. Mass loss from stellar winds creates circumstellar nebulae spanning multiple light-years in diameter, with expelled material forming structures visible to telescopes in distant galaxies as testaments to the star's ongoing evolution. These nebular formations exceed the dimensions of nearby star systems and contribute to galactic chemical evolution across cosmic distances. Material ejected during mass loss episodes forms filamentary structures detectable by telescopes operating in other galactic systems, creating interstellar monuments to stellar evolution that remain visible across millions of years and vast cosmic distances. The expelled material enriches star-forming regions with heavy elements synthesized during stellar nuclear burning phases. Gravitational influence from Stephenson 2T18 remains detectable at distances exceeding 100 astronomical units farther than the orbit of Pluto, yet this enormous sphere of gravitational influence still represents an insignificant fraction of interstellar distances. The star's gravitational reach, while vast by planetary standards, becomes negligible when measured against galactic scales. Compared to the observable universe, Stephenson 218 occupies less volume than a single atom within a cathedral, demonstrating how even the most extreme stellar objects remain infinitesimally small when measured against cosmic dimensions. This comparison reveals the hierarchical nature of cosmic scales, where each level of magnitude dwarfs the previous by factors that exceed human comprehension. Our language and mathematical concepts begin failing when attempting to describe such extremes as human cognition evolved to navigate environments measured in feet and miles, rather than cosmic dimensions that span billions of miles and operate over millions of years. Stephenson 218 demonstrates that the universe operates according to scales utterly impossible for human intuition to grasp naturally. This stellar giant forces us to confront the fundamental limitations of perception that evolved over millions of years to help our ancestors survive in terrestrial environments spanning at most a few dozen miles. Our neural architecture developed sophisticated capabilities for estimating distances between trees, tracking prey across savannas, and navigating landscapes measured in walking days. But these same cognitive systems completely fail when confronted with objects billions of times larger than familiar earthly references. Evolution prepared human consciousness to process objects ranging from inches to miles in scale, creating mental frameworks optimized for survival in environments where the largest structures were mountains and the smallest important objects were seeds or insects. The logarithmic range of sizes that matter for human survival spans perhaps 6 orders of magnitude, from millimeters to miles. Yet cosmic objects exist across scales spanning more than 40 orders of magnitude, from subatomic particles to galactic superclusters. The human brain simply lacks neural circuitry capable of processing cosmic scales adequately, creating a fundamental mismatch between the environments we evolved to understand and the reality we've discovered through scientific investigation. When we encounter objects like Stephenson 218, our minds attempt to apply familiar scaling relationships that break down entirely, leaving us with numbers that carry no intuitive meaning despite their mathematical precision. Even abstract mathematics, humanity's most powerful tool for describing reality, fails to transmit the visceral experience of encountering such dimensions. We can calculate that Stephenson 218 contains the volume of 10 billion suns, but this numerical relationship provides no emotional or intuitive understanding of what such size actually means in experiential terms. Mathematical abstraction allows us to manipulate cosmic quantities symbolically while remaining fundamentally disconnected from their physical significance. Everyday analogies collapse when scale differences exceed factors of billions, leaving us without cognitive bridges between familiar experience and cosmic reality. We might say that if Earth were a marble, Stephenson 2-18 would be larger than a sports stadium. But even this comparison fails, because no human has ever experientially grasped the size difference between marbles and stadiums, in the same direct way we understand the difference between pebbles and boulders. The confrontation with cosmic infinitude generates psychological responses similar to what Immanuel Kant described as the mathematical sublime, where the mind encounters magnitudes that exceed its capacity for comprehension and experiences a mixture of awe, vertigo, and expansion of consciousness. This sublime experience occurs when our faculties of understanding reach their limits and we become aware of something greater than ourselves that nonetheless exists within the realm of natural phenomena. Conceptual vertigo arises when the mind attempts and fails to encompass the totality of phenomena like Stephenson 2-18, creating a disorienting sensation where familiar categories of thought prove inadequate for processing reality. This cognitive vertigo resembles the physical sensation of standing at the edge of a great height, where normal spatial processing breaks down and we become acutely aware of our limitations and mortality. Paradoxically, discovering our cosmic insignificance simultaneously reveals our unique significance as the only known entities capable of measuring and contemplating immensities that transcend all direct experience. While Stephenson 2.18 dwarfs human civilization by factors that challenge mathematical description, we remain the only known observers capable of detecting, studying, and attempting to understand such objects across cosmic distances and temporal scales. Human consciousness possesses the remarkable ability to embrace conceptually what it can never experience physically, allowing us to mentally navigate realities that exist completely outside the boundaries of possible direct encounter. Through mathematics, instrumentation, and abstract reasoning, we extend our awareness across scales from quantum mechanics to cosmology, encompassing domains of reality billions of times smaller and larger than our evolved perceptual capabilities. Our capacity for mathematical abstraction enables navigation through realities that exist far beyond the reach of biological senses, creating conceptual frameworks that allow meaningful interaction with phenomena like Stephenson 2-18, despite the complete impossibility of direct experience. Mathematics serves as a cognitive prosthetic that extends human understanding into domains where evolution never prepared our minds to venture. Scientific instruments represent extensions of human senses that reach across scales forbidden to direct experience, allowing us to detect electromagnetic radiation from objects trillions of times larger than ourselves while measuring their properties with precision impossible through biological perception alone. Radio telescopes, interferometry, and spectroscopic analysis create technological bridges between human-scale awareness and cosmic-scale phenomena. Technology makes us capable of detecting and studying objects that exceed our physical dimensions by factors approaching the ratio between our bodies and individual atoms, demonstrating how human ingenuity can transcend the limitations imposed by biological evolution. The same species that evolved to track animals across African plains now maps stellar surfaces across galactic distances with precision measured in thousandths of arcsecons. Cooperation between human civilizations enables the construction of telescopes spanning entire continents, creating observational capabilities that no individual or isolated community could achieve independently. Projects like the Event Horizon Telescope demonstrate how collective human endeavor can create scientific instruments with resolving power approaching theoretical limits imposed by the wavelength of light itself. Knowledge accumulated across generations reveals a universe progressively more vast and strange than any individual human mind could comprehend independently, with each generation building upon previous discoveries to extend the boundaries of the known into previously unimaginable territories. The cumulative nature of scientific knowledge creates understanding that transcends individual limitations while remaining grounded in human observation and reasoning. Each new discovery demonstrates how little we still understand about fundamental reality, with objects like Stephenson 2.18 revealing gaps in theoretical frameworks that seemed complete just decades earlier. The history of astronomy shows repeated encounters with phenomena that challenge existing paradigms, forcing continuous revision of supposedly fundamental principles about how the universe operates. Stephenson 2.18 has existed for millions of years, slowly evolving through phases of stellar development that predate human civilization by vast margins. Yet only now do we possess instruments sensitive enough to detect and study its properties across the 19,000 light-years separating it from Earth. This temporal gap between stellar existence and human discovery emphasizes how recently we've developed the technological capability to explore cosmic phenomena. Thousands of similar objects likely await discovery in the unexplored depths of space, hidden by interstellar dust, overwhelming brightness of nearby stars, or simple lack of systematic surveys capable of detecting such rare and exotic phenomena. Future observations will undoubtedly reveal stellar objects even more extreme than Stephenson 2.18, pushing the boundaries of possibility further into territories that challenge our most fundamental assumptions about natural law. Future space missions may unveil structures more exotic and impossible than anything currently imagined, as improved instrumentation and novel detection techniques extend our observational reach into previously inaccessible regions of parameter space. The James Webb Space Telescope and next-generation ground-based observatories will likely discover stellar phenomena that make current hypergiants appear ordinary by comparison. Conscious life represents an apparently rare phenomenon in a universe dominated by scales utterly inhuman in their magnitude and temporal duration, suggesting that awareness capable of contemplating cosmic immensity may be among the rarest and most precious emergent properties of natural processes. The ability to experience awe when confronted with stellar giants like Stephenson 2.18 may represent a unique cosmic development. Our capacity for questioning and wonder may constitute a genuinely unique emergent property in a universe otherwise dominated by unconscious physical processes operating across scales and timespans that dwarf biological existence. The ability to feel amazement when contemplating cosmic scales might represent the universe developing a capacity for self-awareness through conscious observers. Perhaps we represent the only known mechanism through which the universe can contemplate itself, making human consciousness a cosmic phenomenon as remarkable as any stellar giant despite our infinitesimal physical scale. Through human awareness, the universe gains the ability to measure, study, and appreciate its own vast structures and complex phenomena. A profound cosmic responsibility emerges from recognition of our privileged position as conscious observers capable of understanding cosmic phenomena, creating ethical obligations to preserve civilization and knowledge that extend far beyond immediate human concerns. If consciousness capable of cosmic comprehension is indeed rare, its preservation becomes a matter of cosmic significance. Preserving human civilization and accumulated knowledge becomes imperative when confronted with the immensity we've discovered, as the loss of conscious observers might eliminate the universe's capacity for self-comprehension. The destruction of human civilization would represent the loss of billions of years of cosmic evolution towards self-awareness. Art, music, and poetry attempt to capture the emotional experience of encountering cosmic sublimity, translating mathematical descriptions of objects like Stephenson 2.18 into forms that resonate with human aesthetic and emotional sensibilities. Creative expression provides pathways for processing cosmic scales that pure rational analysis cannot achieve. Science fiction literature explores the psychological implications of encounters with cosmic vastness, imagining how consciousness might adapt to realities where familiar human scales become meaningless. These creative explorations help prepare human imagination for continued expansion of cosmic awareness. Philosophy must incorporate our new understanding of cosmic scales into discussions about the meaning and significance of existence. Recognizing that traditional frameworks developed when humans believed they occupied the center of a much smaller universe. Modern philosophical inquiry occurs in the context of cosmic immensity that dwarfs all previous conceptions of reality. Spirituality discovers new objects of reverence in the contemplation of cosmic immensity, finding sources of awe and transcendence in scientific discoveries that reveal the true scale of natural phenomena. The encounter with objects like Stephenson 2:18 creates spiritual experiences that no previous generation of humans could access. Humility emerges naturally from recognizing the true scale of reality and our minute place within cosmic hierarchies that extend far beyond human comprehension. Yet, simultaneously, pride arises from our unique capacity to transcend physical limitations through understanding and contemplation. Stephenson 2:18 represents the current frontier of the knowable, but certainly not the boundary of what exists in the vast unexplored reaches of our universe. This stellar giant marks only the edge of our present observational capabilities, beyond which lie countless objects that dwarf even this cosmic monster. The star serves as a humbling reminder that each expansion of our technological reach reveals phenomena more extraordinary than we previously imagined possible, suggesting that the true extremes of cosmic reality remain hidden in territories we have yet to explore. Next-generation telescopes like the James Webb Space Telescope will unveil objects even more extreme than Stephenson 2:18, pushing our understanding of stellar physics into previously unimaginable territories. With infrared capabilities that penetrate interstellar dust and spatial resolution approaching theoretical limits, JWST will detect stellar giants hidden in the dusty star-forming regions where the most massive objects are born. These observations may reveal hypergiants that make Stephenson 2:18 appear ordinary, forcing yet another revision of our concepts about maximum stellar sizes. The extremely large telescope, with its revolutionary 130-foot primary mirror, will possess resolution sufficient to study atmospheric details of stellar surfaces across entire galactic distances. This ground-based observatory will provide direct imaging capabilities that can resolve features on hypergiant photospheres, allowing astronomers to map convection cells, atmospheric dynamics, and mass loss processes in real time across cosmic distances that currently permit only statistical analysis. Space-based interferometry will eventually enable direct imaging of stellar surfaces in distant galaxies, revealing hypergiant populations in environments with different metallicities, star formation histories, and physical conditions than those existing in our local galactic neighborhood. These observations may discover stellar configurations that cannot form under the conditions prevalent in the Milky Way, expanding our understanding of possible stellar physics beyond the constraints of local cosmic chemistry. Each technological advancement expands the horizon of the observable universe while simultaneously revealing new categories of the unknown, demonstrating that scientific progress creates knowledge and mystery in equal measure. Every answered question about objects like Stephenson 2:18 generates multiple new questions about phenomena we couldn't even conceive before possessing the observational tools to detect them. The expansion of human knowledge proceeds like the exploration of an infinite fractal coastline, where each step forward reveals new complexities that exceed the boundaries of current understanding. Fundamental physics may require complete revision when confronted with phenomena operating at the extreme scales represented by objects like Stephenson 2:18. where matter behaves according to principles that extend beyond the regimes where current theories have been tested. The physics governing stellar structure in environments where density approaches laboratory vacuum while maintaining stellar temperatures and chemical complexity may operate according to laws that current theoretical frameworks cannot describe or predict. General relativity and quantum mechanics have never been tested experimentally in regimes of ultra-low density combined with extreme temperatures and strong radiation fields characteristic of hypergiant atmospheres. The behavior of matter under these conditions may reveal new physical principles or demonstrate breakdown of theoretical frameworks that appear universally valid within the limited parameter ranges accessible to terrestrial experimentation. Modified theories of gravity may prove necessary to explain the stability and structure of hypergiants like Stephenson 2-18, where conventional gravitational physics struggles to account for the observed combination of enormous size, low density, and apparent structural stability. Alternative gravitational theories that include additional fields or modified force laws may provide better descriptions of matter behavior in these extreme environments. New states of matter may emerge under the exotic conditions of pressure, temperature, and radiation density that characterize hypergiant interiors and atmospheres, creating phases of matter that exist nowhere else in the observable universe. These exotic matter states could possess properties that fundamentally alter stellar structure and evolution, explaining the existence of objects like Stephenson 2-18 that appear impossible according to conventional physics. Life as we understand it cannot exist anywhere within hundreds of light years of objects like Stephenson 2-18, where intense radiation fields would sterilize planetary surfaces and prevent the complex chemistry required for biological processes. The radiation environment around hypergiants creates zones of biological impossibility spanning volumes larger than entire stellar neighborhoods, demonstrating how the most extreme stellar objects fundamentally alter their cosmic environments. The sterilizing radiation from Stephenson 2-18 would destroy any complex molecules across distances exceeding 300 light-years, creating vast regions where biological chemistry cannot proceed, and planetary atmospheres would be stripped away by stellar winds and high-energy photons. These dead zones around hypergiants represent some of the most hostile environments in the galaxy for any form of life based on chemistry familiar to terrestrial biology. Advanced civilizations operating on cosmic scales might deliberately use hypergiants as navigational beacons for intergalactic travel, exploiting their enormous luminosity and distinctive spectral signatures as reference points visible across millions of light-years. Objects like Stephenson 2-18 could serve as cosmic lighthouses that enable navigation through the vast emptiness between galactic clusters, providing fixed reference points in an expanding universe. Future stellar engineering might deliberately modify hypergiant evolution to create artificial signaling systems detectable across cosmic distances, using controlled mass ejection episodes or atmospheric manipulation to generate distinctive variability patterns that carry information across intergalactic space. Such technology would operate on scales and time spans that make terrestrial engineering appear microscopic, yet remain conceivable within the framework of physics as we currently understand it. The Fermi paradox acquires new dimensions when we consider scales of engineering that could manipulate stellar evolution across galactic distances and geological timescales, suggesting that our search for extraterrestrial intelligence may be limited by anthropocentric assumptions about appropriate scales for technological development. Civilizations operating on cosmic scales might create artifacts and signatures completely beyond our current conceptual frameworks for recognizing artificial phenomena. Our search for extraterrestrial intelligence remains constrained by preconceptions about appropriate scales and time spans for technological development, potentially causing us to overlook evidence for civilizations that operate according to principles we cannot currently imagine. The existence of objects like Stephenson 2:18 challenges us to expand our concepts of what constitutes possible technology and recognizable intelligence. Phenomena that we attribute to natural stellar evolution might actually represent technological artifacts created by civilizations operating on scales of stellar engineering that dwarf human technological capabilities by factors comparable to the difference between ant colonies and space agencies. The distinction between natural and artificial phenomena may become meaningless when considering technologies that can manipulate stellar structure across cosmic distances and geological timescales. Stephenson 2:18 might represent the product of cosmic engineering by civilizations operating across geological timescales, using technologies that can modify stellar evolution to create objects serving purposes we cannot currently comprehend. Alternatively, this stellar giant might exemplify exotic physics still undiscovered by terrestrial science, revealing natural processes that operate according to principles extending far beyond current theoretical frameworks. Both possibilities force fundamental reconsideration of our understanding of reality, whether through recognition that advanced technology can achieve scales we consider impossible, or through discovery that natural physics operates according to laws more complex and surprising than our current theories suggest. Either revelation would revolutionize human understanding of cosmic possibilities and our place within them. Scientific education must prepare future generations to navigate conceptually between atomic and cosmic scales, developing cognitive frameworks that can meaningfully engage with phenomena spanning dozens of orders of magnitude in size, energy, and temporal duration. Cosmic literacy becomes an essential capability for citizens of technological civilizations that must make decisions affecting cosmic-scale phenomena while remaining grounded in human-scale values and experiences. The ability to think coherently across scales from quantum mechanics to cosmology defines a new form of intelligence required for species that have developed technologies capable of detecting and potentially influencing cosmic-scale phenomena. This multi-scale cognitive capability represents an evolutionary development in human consciousness that may prove as significant as the original development of language or abstract mathematical reasoning. Contemplation of objects like Stephenson 2:18 cultivates intellectual virtues of curiosity and humility, essential for continued scientific progress, creating psychological attitudes that embrace mystery and uncertainty as opportunities for discovery rather than threats to understanding. The emotional experience of encountering cosmic sublimity develops character traits that enhance both scientific capability and human wisdom. Accepting our fundamental ignorance about cosmic-scale phenomena liberates the mind for exploration without preconceptions, allowing scientific investigation to proceed according to observational evidence rather than theoretical expectations. The recognition that current understanding represents only the earliest stages of cosmic exploration creates freedom for discovering principles and phenomena that extend far beyond present conceptual frameworks. Emergent beauty arises when we embrace cosmic mystery rather than demanding immediate explanations for every observed phenomenon, finding aesthetic and emotional satisfaction in the process of exploration itself rather than only in the achievement of complete understanding. The contemplation of cosmic scales generates experiences of beauty and transcendence that enrich human consciousness independent of their practical applications. Appropriate reverence before cosmic immensity does not diminish human dignity, but amplifies it by revealing our unique capacity for transcendent awareness that extends far beyond the biological limitations of our physical existence. The ability to contemplate and appreciate cosmic beauty represents a cosmic achievement as remarkable as any stellar phenomenon. We represent stellar material that has achieved consciousness capable of contemplating the origin and destiny of stars themselves, embodying the universe's development of self-awareness through biological evolution and technological development. Human consciousness allows the cosmos to study and appreciate its own vast structures and complex evolutionary processes. Our physical insignificance contrasts dramatically with our conceptual and emotional grandeur, demonstrating that cosmic significance cannot be measured through spatial or temporal scales alone, but must include the capacity for understanding, appreciation, and transcendent experience that consciousness brings to cosmic phenomena. In the end, the true miracle is not that Stevenson 2:18 exists in defiance of theoretical expectations, but that conscious observers exist to discover, study, and appreciate such cosmic wonders, despite our infinitesimal place in the vast hierarchy of cosmic scales. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.